All right, so now let's look at another application. Application of squeezing theorem. So if you remember, the squeezing theorem says that, if you have one function squeezed between two other functions, if the limit of smaller and bigger function are the same number, then the limit of the middle function is also existence equal to the same number. So we used it to calculate limit sine x over x. Now another type of limit we can calculate with squeezing theorem. Find limit x squared sine 1 over x as x approaches to 0. So before solving this question, I want to give you a reminder that we saw before that limit sine 1 over x as x approaches to 0 does not exist. And I think maybe the one we looked at was like pi over 2 over x, something like that. But again, the same idea that we use there can be applied to show that the limit sine 1 over x itself also does not exist. So you can write the details yourself. I think you can look at the solution for the question that we did for sine pi over 2 over x. Look at the idea that we use to show this limit does not, even the one-sided limit does not exist. Use the same idea to show that this limit does not exist either. So limit sine 1 over x does not exist as x approaches to 0. But limit x squared times this function, x squared times sine 1 over x exists. So that's what we want to show using squeezing theorem. How can we do that? So for applying squeezing theorem, we need to squeeze our function between two other functions, a smaller function and a bigger function. So how can we squeeze this function between two other functions? We can use the fact that sine 1 over x is always between -1 and 1, right? So note that sine 1 over x is between -1 and 1 for all x not equal to 0, right? I mean, for x equals 0, this is undefined because 1 over 0 is undefined. But for every other number, sine 1 over x is sine of some number, some angle or some number, and sine is always between -1 and 1. So sine is always in -1 and 1. Now, what we have here, the expression we have is x squared times sine 1 over x. So why don't we multiply everything by x squared? So thus, minus x squared less than equal to x squared sine 1 over x, and this is less than equal to x squared. Again, this is true for all x not equal to 0. So note that x squared is bigger than 0 for x not equal to 0, right? X squared is always non-negative. It's 0 if x is 0, and otherwise it's positive. And right now we can assume, of course, x is not equal to 0 because limit, we calculate the limit as x approaches to 0, and x approaches to 0 means, as you know, x gets very close to 0 but not equal to 0. So so x squared is positive. So if we have an inequality and we have a positive number, we can multiply all sides of the inequality by our positive number. So we can multiply everything by x squared. And we get minus x squared less than x squared times this less than x squared. So yeah, if you have a positive number, we can multiply the inequality, both sides of the inequality by your positive number, and the inequality will be unchanged, right? So less than equal remains less than equal, or greater than equal remains greater than equal. But if you have a negative number, this is just a fact from pre-calculus. If you have an inequality, you multiply both sides with a positive number, inequality remains unchanged. And if you have a negative number, you multiply both sides with a negative number, the inequality flips. So less than equal becomes greater than equal, or greater than equal becomes less than equal, and so on. So note this. So the inequality will not flip. Will not flip when we multiply both sides by x squared. So right now we have our function squeezed between two other functions. So now we can say that limit minus x squared is equal to limit x squared as x approaches to 0, and this one x approaches to 0. These are 0. So the smaller function here, minus x squared, and bigger function here, x squared. Both of these functions at x equals 0 have limits 0. So the middle function must also have the limit of the middle function must also exist. So thus, by squeezing theorem, limit of the middle function, x squared sine 1 over x, x approaches to 0, exists, right? And is equal to 0. Because smaller function, bigger function have limit 0. So middle function, the limit of it also exists and is equal to 0. Okay, so one exercise I can give you, show that limit x times sine 1 over x, x approaches to 0, also exists and is equal to 0. Hint, consider the left limit and right limit separately first. So first consider the left limit and right limit separately. See, in the previous example, we did not have to consider left and right limits separately first, because we could just squeeze our function between two other functions, smaller function and bigger function, and then apply squeezing theorem. And the reason was that, we multiplied, we had an inequality, we multiplied everything by x squared, which was a positive number, and the inequality remained unchanged. But here, when you want to multiply everything by x, to get you have it again, you can, of course, you can again start with sine 1 over x being between -1 and 1. Then you have to multiply everything by x. Now, when you multiply by x, x approaches to 0, right? So x could be either positive or negative. If x approaches to 0 from right, x will be positive. If x approaches to 0 from left, it will be negative. So that's why we have to consider two cases: right limit for the case where x is positive, left limit for the case where x is negative. So calculate each of these limits separately, apply squeezing theorem for each of these functions. And once you have the left limit and right limit, once you show that each of left limit and right limit exists and is equal to 0, then you can say that the whole limit also exists and is equal to 0. Okay, so the difference with this example is that this example, we multiply everything by x squared, which is positive number. So the inequality will not flip. But here, when you multiply with x, well, if x is positive, the inequality will not flip. But if x is negative, the inequality will flip. But in any case, you will see that you can still show that, the right limit and left limit, each of them are 0, and therefore the whole limit will be also 0. All right. So these are some examples of squeezing theorem. Now let's move on to the next topic, which is limits at infinity. And ultimate behavior of the function. So ultimate behavior or end behavior, sometimes also called end behavior of a function. End behavior of functions. So the goal here is, let's say, given a function f of x, want to know whether the outputs get closer and closer to a fixed number L as the values of x get bigger and bigger. So get bigger and bigger either with positive sign or with a negative sign. Okay, so the definition here is that we say that limit f of x as x approaches to infinity equals L if the outputs get closer and closer to a number L as the inputs get bigger and bigger with positive sign. So for example, if the inputs become 10, how much is the output? Then let's say input becomes 100, how much is the output? Then the input becomes 1000, how much is the output? And so on. So similarly, we say that limit f of x as x approaches to minus infinity equals L. Again, if the outputs get closer and closer to a fixed number L, as the inputs become larger and larger, with a negative sign. So for example, input is minus 10, how much is the output? Then input is minus 100, how much is the output? Minus 1000, how much is the output? And so on. Okay, and in either case, whether the limit at infinity is L or whether the limit at minus infinity is L, in either case, we say that y equals L is a horizontal asymptote. So definition, we say y equals L is a horizontal asymptote of y equals f of x if limit at infinity is L or limit at minus infinity is L. If either the first thing happens or second one happens, then we say that y equals L is a horizontal asymptote. So let's look at an example. Let's say f of x equals 1 over x. Find limit 1 over x as x goes to infinity and limit 1 over x as x goes to minus infinity. Okay, so limit, so for the first one, for limit 1 over x as x goes to infinity, so we have to let x become larger and larger. Let's say if x is 10, then 1 over x will be 0.1. If x is 100, then 1 over x will be 0.01. X is 1000, 1 over x will be 0.001. Right? So as the inputs x become larger and larger, the outputs become smaller and smaller, and they become closer and closer to 0. Right? So the outputs become closer and closer to 0 as x goes to infinity. So we can say that limit 1 over x as x goes to infinity is equal to 0. Similarly for the other side, similarly, check that limit 1 over x as x goes to minus infinity is also 0. So the graph would look like this. See, we had, if you remember, we had vertical asymptote at x equals 0. And as x goes to infinity, f of x approaches to 0. And also as x goes to minus infinity, f of x approaches to 0. So let me explain here. So when we say x approaches to infinity, limit f of x is 0, means the outputs become very close to y equals 0. Y equals 0 means x-axis, right? So as x become larger and larger, which means if you're on the very right side or to the right end of your graph, then the outputs become very close to 0, meaning that very close to x-axis or y equals 0. Similarly, on the other side, as x values become smaller and smaller, so minus infinity means, very left, then again, the outputs become very close to 0, so very close to x-axis. And so that's why y equals 0 here is called horizontal asymptote. So horizontal asymptote because it's a horizontal line, and asymptote because the graph gets closer and closer to that line, but it will never touch it. And for x equals 0 here, so this is a vertical asymptote, meaning that, if x values become very close to this line here, then the y values, so previously we saw this, right? If x approaches to 0 from right, y value goes to infinity, meaning that it becomes higher and higher. And from left limit, x approaches to 0 from left, y values approach minus infinity, which means, low become lower and lower, so with a negative sign. Okay, so vertical asymptote we saw before, and here we saw that this also has a horizontal asymptote at y equals 0. So we can say that y equals 0 is a horizontal asymptote for y equals 1 over x. Okay. So this is one simple example for horizontal asymptotes and limits at infinity. All right, so 1 over x, the limit 1 over x, so ultimate behavior or end behavior of this function. So this is also called end behavior. Okay, so end behavior. I could also mention here, note limit f of x as x approaches to infinity and limit f of x as x approaches to minus infinity are called the end behavior or end behaviors, because 2 of them, of f of x. Okay, so here in this example, as x approached infinity or minus infinity, the outputs became closer and closer to some fixed number L. But sometimes as x approaches to infinity or x approaches to minus infinity, the outputs become larger and larger or become smaller and smaller. So infinity limits at infinity. So we say that limit f of x as x approaches to infinity equals infinity if the outputs of f of x of f become arbitrarily large as x approaches to infinity. Meaning that as x becomes larger and larger, as the input x become larger and larger, similarly, we say that limit f of x as x approaches to minus infinity equals infinity if the outputs of f become arbitrarily large as the input x become larger and larger with a negative sign. Similarly, the other limits, limit f of x as x goes to infinity equals minus infinity, and limit f of x as x goes to minus infinity equals minus infinity can be defined. Okay, so let's look at an example. Let's say find limit x to power n as x goes to infinity. Here, n is a positive integer, or n is a natural number. Let's say n is a natural number. Okay, so limit x itself as x goes to infinity. So if, let's say, n is 1, so limit x as x goes to infinity is infinity, right? Why? Because, if you look at the inputs and outputs, let's say if x is 10, f of x will be 10. If x is 100, f of x will be 100, and so on. Right? So as the inputs become larger and larger, the outputs also become larger and larger. So the limit at infinity is infinity. And similarly, check that the limit x as x goes to minus infinity is minus infinity, or limit x squared as x goes to infinity is infinity. Limit x squared as x goes to minus infinity is again infinity, right? Because power 2 kills the minus sign, right? So x approaches to minus infinity means what? It means like minus 10. Then how much is the output? Minus 10, the whole squared is 100. And then if x is minus 100, then output will be minus 100, the whole squared. Again, a positive big number, right? So as x becomes larger and larger with a negative sign, output becomes larger and larger with a positive sign. So yeah, these limits are infinity. What about x cubed? X cubed as x goes to infinity is infinity. And limit x cubed as x goes to minus infinity is minus infinity. See, there's power 3 here, which will keep the minus sign. So if x is minus 10, then minus 10, the whole cube is the output. If x is minus 100, minus 100, the whole cube is the output, and so on. So in general, we can say limit x to power n equals infinity as x approaches to infinity for any n in any natural number n, like 1, 2, 3, and so on. And for the limit at minus infinity, we can say that the answer is infinity if n is an even number and is equal to minus infinity if n is an odd number. Okay, so these are the n behaviors of this function x to power n. So what about for polynomials? So n behavior of polynomials. So to find the n behavior of a polynomial, factorize from the highest power of x. Factorize from the highest power of x. So see, for P of x equals x cubed minus x squared plus 5x. Find the limit P of x as x goes to infinity and limit P of x as x goes to minus infinity. Okay, so as x goes to infinity, what happens? So limit and P of x as x goes to infinity means limit x cubed minus x squared plus 5x as x goes to infinity. So first you can replace x with infinity to see what happens. Let's say if I replace x with infinity, I'll get infinity cube minus infinity squared plus 5 times infinity. So this is infinity minus infinity plus infinity, right? Infinity cube means a very large number to power 3 is infinity. Infinity squared, a large number to power 2 is infinity. 5 times a very large number is also infinity, right? So infinity minus infinity plus infinity. Some people think that they can cancel this with this, but that's not true. Infinity minus infinity is one of the indeterminate forms. So infinity minus infinity is not 0, is not infinity either. It's not a fixed number either. So it's indeterminate, meaning that the answer potentially could be anything, depends on the type of the function. So infinity minus infinity is an indeterminate form. I.e. the answer could be anything depending on the example, like other indeterminate forms. We need to simplify to compute this type of limits or these limits. Okay, so to compute infinity minus infinity, or like any other indeterminate forms, we have to simplify. So here simplifying, so we know simplifying depends. We saw, for example, trigonometric functions. Simplifying means you have to connect it with limit sine x over x and etc. Now for limit of a polynomial as x goes to infinity or minus infinity, simplifying means factorizing from highest power of x. So to simplify, factorize from x cubed. So then what do we get? We get limit x cubed times 1 minus 1 over x plus 5 over x squared as x goes to infinity. So it seems the screen again is freezed. So let me stop share and share again. Yeah, so this limit will be infinity. Now see limit 1 over x which is same as limit 5 over x squared. So these limits will be 0 as x goes to infinity, 1 over x or 5 over x squared. So it's a constant over infinity. So those limits will be 0. So the answer will be infinity times 1 minus 0 plus 0. And infinity to power 3 we said is infinity, right? So the answer will be infinity. So note that, infinity plus infinity is infinity, or infinity times infinity is infinity. Infinity times minus infinity is minus infinity, right? So infinity plus infinity is not indeterminate, because infinity plus infinity means a very large number plus another very large number. Of course, the answer will be very large. But when you have a very large number minus another very large number, then the answer could be anything potentially. So for example, 1 million minus 1,000 is a very large number, but 1 million minus 10 million is a very large number with a negative sign, or 1 million minus 999,000 and 1 million minus 999,999 is just 1, right? So that's why we say potentially could be anything. The answer could be 1, it could be infinity, it could be minus infinity, or 1 million minus 1 million is just 0, right? So the answer could be 0 as well, potentially. So depends on, so when you say very large number minus very large number, depends how large is the first number compared to the second number. Are they equally large, or the first number is larger? So then the answer could be different. But when you say infinity plus infinity, a very large number plus a very large number, the answer will be always very large. So yeah, infinity. So please have these rules in mind. Or infinity times infinity means a very large number multiplied by another very large number. The answer will be, of course, very large, and so on. So infinity minus infinity, we said, is indeterminate. Right. So for example, as I said, 1 million minus 1 million is 0, but 1 million minus 1,000 is 999,000, which is infinity, right? Or 1 million minus 10 million. This is minus 9 million, which is minus infinity, and so on. So similarly, you can check that infinity over infinity is also indeterminate. Again, like 1 million over 1 million is 1, but 1 million over 10, for example, is 100,000. So again, depends how large the first number is compared to the number in the denominator. Are they equally large, or first number is larger? What is the situation? So infinity minus infinity is indeterminate. Infinity over infinity is indeterminate. So we will see more indeterminate forms later. So far, the most important indeterminate forms that we have seen are 0 over 0, infinity over infinity, and infinity minus infinity. And the other forms, infinity plus infinity, infinity times infinity, and so on. So these are not indeterminate, and the answer can be computed. Okay, so now for this function, the polynomial that we had, so we calculate the limit at infinity, and it turns out to be infinity. What about the limit at minus infinity? So back to example above. Limit p of x as x goes to minus infinity. This is limit x cubed minus x squared plus 5x as x goes to minus infinity. And this is limit x cubed times 1 minus 1 over x plus 5 over x squared as x goes to minus infinity. And then this is minus infinity cube times 1 minus 1 over minus infinity plus 5 over infinity. So the answer will be minus infinity times 1 minus 0 plus 0. And the answer is minus infinity. So a constant over infinity, I can also include it here. Constant over infinity, this is 0. Now a constant times infinity will be infinity if constant positive, and minus infinity if constant negative. So these are determined. Constant over infinity, like for example, 5 over 10,000 or 5 over 1 million. It's a very small number for sure, right? So constant over infinity is 0. Constant over minus infinity similarly is 0. Constant times infinity, like 5 times infinity is infinity. Like 5 times a very large number is a very large number. Minus 5 times infinity is minus infinity, because minus 5 times a very large number is still very large, but with a negative sign. So minus infinity, and so on. Okay, so this limit, so at infinity, the limit is infinity. At minus infinity, the limit was minus infinity. Now, remark to compute the limit at infinity of rational numbers, of rational functions, factorize from the highest power of x, the highest power of x in top, and the highest power of x in bottom. So for example, find limit x cubed plus x squared minus 6x divided by let's say 2x to power 4 plus x cubed minus 7 as x goes to infinity. So we have to factorize from highest power of x in top and highest power of x in bottom. So what do we get? For polynomials, just factorize from highest power of x, like the example we saw. Now for rational functions, so see here, it was a polynomial, we factorize from x cubed, which was highest power of x. But for rational function means one polynomial divided by another polynomial. So for the polynomial of top, just factorize from highest power of x in top. For the polynomial in bottom, factorize from highest power of x in the bottom. Then what do we get? We get limit x cubed plus x squared minus 6x divided by 2x to power 4 plus x cubed minus 7, x goes to infinity. So we are going to take x cubed out. Highest power of x is x cubed in top. 1 plus 1 over x minus 6 over x squared divided by x to power 4, and then 2 plus 1 over x minus 7 over x to power 4, x goes to infinity. And then I can simplify this. So this one cancels with this, and just one x factor will be left in the bottom. And then I'm going to have, so limit 1 plus 1 over x minus 6 over x squared divided by x times 2 plus 1 over x minus 7 over x to power 4, x goes to infinity. So this is 1 plus 1 over infinity minus 6 over infinity, infinity times 2 plus 1 over infinity minus 7 over infinity. So a constant over infinity, remember we said constant over infinity here. Constant over infinity is 0. So all these are 0. So it's going to be 1 plus 0 minus 0 divided by infinity times 2 plus 0 minus 0. That is 1 over 2 times infinity. 2 times infinity is also infinity. 1 over infinity, again, constant over infinity, we said 0. So we concluded that limit of this function x cubed plus x squared minus 6x divided by x to power 2x to power 4 plus x cubed minus 7 as x goes to infinity is infinity, and therefore we can say that y equals 0 is the horizontal asymptote of this function. Okay, so if the limit at infinity or minus infinity is 0, so similarly, so also check that the limit at minus infinity is also 0. So we can do the very similar calculation for the limit at minus infinity, and you will see that that limit is also 0. All right, so here both limits at infinity and at minus infinity, the limits are 0. But even if one of them was 0, we could still say that y equals that number. So y equals this number is called the horizontal asymptote of this function. So horizontal asymptote, horizontal because the horizontal line, y equals the number is a horizontal line. And asymptote because the graph will get closer and closer to that number, but it won't touch it. So this function, to sketch the graph of this function right now, it's, I think, too soon. Once we develop some tools, for example, derivatives, we can sketch some rational functions. This is still, even after we develop those tools, sketching these functions will be a little bit challenging. But you could also use for now, you can use graph calculators to sketch the graph of this, and you will see that y equals 0, meaning x-axis will be horizontal asymptote, which means as x gets very larger, become larger and larger with positive sign, or larger and larger with negative sign, the outputs become closer and closer to 0, very close to x-axis, or y equals 0. Okay, guys, so this is the concept of the limits at infinity and the end behavior of the functions. So maybe next time I can do a few more examples of this section and limits at infinity to see how we can. So I right now explained how to handle like a rational function. So maybe we can do a few more examples of this type, or some other functions, limit at infinity of some other functions. Okay, guys, so thank you, and see you next time.